In this lesson, we're going to talk about linear functions. A linear function has a pretty simple definition. It's a function, and it's a line. Surprise! So anyway, a linear function, though, we want to work out the equations that match up with it. These functions have a constant change in function value for a constant change in x. We often associate that with the word slope, or the steepness of the line. The slope of the line, it's a ratio of the rise to its run, but a lot of times you'll see it written this way. Rise over run. And again, that value is constant, no matter what values of x you're dealing with. Here's our first example. We have a table of the winning height in inches of the winning pole vault in the men's Olympics for the years 1900 through 1912. Now this function is linear, but why? Let's notice that the years go up by 4, as this is the Olympics we're talking about. But the height of the winning pole vault goes up by 8 each time. Now why is this linear? Because every constant change in x gives you a constant change in y. So that's why this function is linear. The height has a constant change for a constant change in time. Now to write a formula for this, let's give these things names. Let's let the height be h, and for t, we will let it be the number of years after 1900. It's often a good idea to do this because then when t equals 0, you're looking at your first piece of data. Now, the slope is the ratio of its rise to its run. So for the slope, we can just do that very thing. Rise is the change in the dependent variable, the h in this case. So you're looking at 8. And then your run is the change in time, which was 4. And that gives us 2. Now it might be nice to put a couple of units on here. 8 was in inches, and 4 was in years. So the slope of this line is 2. Now to write a final value, the easiest thing to do is say the height is equal to, and since I let t equal 0 correspond to the starting point, that just means we'll have a starting point of 130. And then we're going to have plus some change in inches per year times the number of years. Now here's one of the problems with models. If we were to continue doing this, then the winning height in the 2016 Olympics, if we were to just plug in 116 into that formula, it would have been 29 feet and 8 inches. Now that's really high, but it was only 19 feet 9.4 inches in the 2016 Olympics. So mathematical models, if you're going to use them, make sure that the domain is really specified to be meaningful for where the data is coming from. If you extrapolate too far, you might get extremely inaccurate predictions. Now here's one that has been holding pretty well. The world record time to run a mile has been decreasing according to this formula, where t is in years since 1900, and y is the number of seconds to run that mile. So now let's give some interpretations of these values. First off, the 260. Just like in the last example, that's associated with t equals 0. When t equals 0, we're talking about 1900, so the world record time to run a mile was 260 seconds in 1900. Now as for the slope is negative, which means that this time is decreasing. What does that mean? Well, it's decreasing by this amount, this negative 0.4, every single year. So a lot of times when we interpret a slope, we'll just look at it as a number out of one unit of the dependent variable, in this case the year. The world record time to run a mile has decreased by 0.4 seconds each year. Notice that I didn't write negative 0.4. Instead, I gave it a practical way to say it. It decreased by that amount instead of saying it changed by negative 0.4. Now to talk about the slope in a little bit more of a formulaic fashion, we often use the Greek letter capital delta. And so that triangle is just simply a symbol that we use to represent change in. So where I write delta x, I'm referring to some change in x. And delta y is some change in y. Now I already told you that slope is rise over run. So rise is going to be a change in y, and run is going to be a change in x. We often could write this as f of x2, that's the y value associated with x2, and f of x1 is the y value associated with x1. oftentimes you've run across this formula as m equals y2 minus y1 over x2 minus x1. We usually can call this thing a difference quotient. That's a term we don't have to dig too deep on, but it helps us define derivatives later. And this delta y over delta x we will often just call a rate of change, or sometimes we might use the term average rate of change, which we'll talk about later. In this context, the unit of a slope is always the y units over the x units. Now, we already sort of alluded to this fact in our first example, but a linear function will have the form f of x is equal to b plus mx. B is the vertical intercept, or better said, the starting point, and m is the slope, that constant value. We like to write it in this fashion because it makes more logical sense if you think about the applications. You have a starting point, and then you show how it's changing. Both ways are acceptable, b plus mx or mx plus b. But for this book, we'll start with this b plus mx idea. Note that if this slope is positive, then you get an increasing function, and if the slope is negative, you get a decreasing function. And if you happen to get 0 for this m, that makes it disappear entirely, and you just get y equals b, the standard equation of a horizontal line. Now, one way to get an equation the easy way is to use what we call the point-slope formula. If you're looking at a line that has slope m, and it passes through some given point or found point, x0, y0, then you can use this equation to find the equation of that line. Let's make a quick example as to why this works. Consider a line with slope m that passes through x0, y0, and some point xy on the line. Now this xy is sort of a random point. It just represents some point on the line that you would want to be able to work with, and it helps define the equation. Now, for the sake of my slope equation, let me actually call this thing x1, y1 and x2, y2. Now remember, the equation for slope is m is equal to y2 minus y1, that would be y minus y0, over x2 minus x1, which would look like x minus x0. Then what I'm going to do is multiply both sides of this equation by x minus x0, and the goal is to clear out the denominator in doing so. Notice that these cancel, and if I just rearrange the order of things a little bit, let's put the y minus y0 first, and then you've got the x minus x0 times m. I'll just switch that order as well. And there you have it. That's the exact equation that I told you. So the point-slope formula is actually nothing more than a rewriting of the slope formula that we already have. Let's do an example. The solid waste generated in the cities of the US is increasing every year. So let's take a look at a little bit of data, and then let's see if we can predict a few things. Let's assume that this is a linear function and find a formula. I'll start off by letting t be the number of years after 2000. Note that this says the solid waste is a linear function of time. Remember, y is a function of x. So let's say w is a function of t. That means t is your independent variable, like your x, and w is your dependent variable, like your y. So I can turn my data into some points. In 2000, we're looking at 0, 238.3 as our first data point, and in 2006, we have 6, 251.3 as our data. So let's find the slope from this. M is equal to 251.3 minus 238.3 over 6 minus 0. The numerator simplifies to 13, and the denominator simplifies to 6, and I think I'll leave that as a fraction just to make this easier. Now, I actually don't have to use the point-slope formula this time, because I'm given a nice benefit. This value, because it's associated with 0, is my b. There's nothing I have to solve for to find b. So consequently, we can say that the waste is equal to, remember it's b plus mx, 238.3 plus mx, 13 over 6, and we'll say t because that's my variable. Now let's use this to predict the amount of solid waste generated in the year 2020. Now here's some interesting insight. 2020, as you guys all know, was a very unusual year. So whether this prediction is correct would be an interesting thing to find out. To do this, I'll plug in 20 into my formula. 238.3 plus 13 over 6 times 20. If I run that through the calculator and approximate it a little bit, we'll get 281.63. And this is again in millions of tons of garbage. Try looking up this fact. See how close it is to the actual value of what happened in 2020.